This video is going to show you how you can use the GPIO protocol to get input into your Android Things application. We'll discuss the Raspberry Pi Rainbow Hat and its sensors, in this case the capacitive buttons, using them to gather input for later use. Let's get started. GPIO stands for General Purpose Input Output. GPIO works with a single pin on your board and it can have two states, on or off. This means you can monitor a GPIO pin and know when it changes state, or you can change the state of the pin yourself. Monitoring state changes is known as GPIO input, and changing the state is known as GPIO output. Input is reading the pin and output is writing the pin. This may seem counterintuitive at first, but consider it from the GPIO peripheral's perspective. If we read the GPIO pin, that is input into our application. If we write to the pin, that is output to the peripheral. Our Raspberry Pi is now plugged in and connected via ADB, ready for development. We have the Rainbow Hat connected to the top of our Raspberry Pi. This hat has a lot of peripherals, and amongst them 3 capacitive buttons. We are going to code our app so that when one of these buttons is pressed, a logcat message appears. Here are the 3 buttons, and here is button A that we want to program. When working with the Rainbow Hat, we can see how each of the peripherals on the hat is connected to our Raspberry Pi by looking at the pinout diagram. To understand how each peripheral works and determine the protocol needed to talk to it, we should consult the Rainbow Hat documentation and, if needed, the specific peripherals datasheet. In the documentation shown here, we can see the 3 capacitive buttons are described as 3 touch inputs that use the AT42Q2 1070 controller. You don't have to worry about this controller, just understand that this is used to make the capacitive buttons work as expected from a hardware perspective. The table here shows that the buttons use GPIO pins BCM 16, 20 and 21. This is the hint we need to tell us to use GPIO protocol for our communication with the buttons. Now let's double check the pin we need to use by referencing the Rainbow Hat pinout diagram. Looking at this diagram, we can see at the bottom there are the details of the 3 capacitive touch buttons. Let's choose to code button A. This has the pin address BCM21. We should remember this for later reference. Okay, let's program the button. Here I have an Android Things project already set up in Android Studio. If you aren't sure how to get your project to this point, you can revisit the previous first app lesson for instructions. First, we create an instance of Peripheral Manager Service using this code. This is the Android Things SDK class that allows us to open connections to different board pins using the different available protocols. Using this instance, we want to open a GPIO connection with the pin address we saw earlier on the pinout diagram. When we open this connection, we are given back a GPIO bus variable that will now allow us to communicate using the Android Things SDK GPIO class. We'll use this variable in multiple Android activity lifecycle methods, that's why we make it a field. Notice that we have to wrap the open GPIO call in a try-catch block. This is because the method, and most other methods we will use in the future, all throw a potential IO exception. This is due to the fact that we are dealing with hardware, and at any moment the pin or the peripheral could become unavailable, for instance because of a loose wire. At that point, calling the method would throw this exception. We are assuming that all our wires are nicely connected, and if we do get one of these IO exceptions, it would be really bad for our app, and actually we want to crash straight away, so we can diagnose the problem as soon as it happens. That's why in the catch block we throw an illegal state exception, as we are not expecting nor wanting this to happen. This is known as failing fast, and is a clean code best practice. The benefit of this is our bus variable is either a fully instantiated field at this point, or our app has crashed. Therefore, from this point on, there is no need to check if our bus field is null, it never is. Opening a connection to a pin is capturing this pin as your resource, and like with all resource management, it is good practice to release resources once you have finished with them. Also, if we have an open connection to a pin, no other code can open a connection to that same pin until we close our connection. Since we open the connection to our pin in the onCreate method, we should use the symmetrically matching pair with the Android lifecycle to close the connection. Therefore, we close the GPIO bus connection in onDestroy using this code. Again, close can throw an IO exception. We don't do anything about this if we get an exception, but we can log it out so that we know next time our app starts if something unexpected had happened in the past. Once we have a connection to the GPIO bus, we now have to configure our pin for GPIO input from a button. We set the direction to in using this code. This means we are telling the GPIO bus that we expect to use this pin as an input, i.e., we expect to receive information from the peripheral on this pin. We set the active type to low using this code. If you remember the reference document, the document describes the touch input setup. You can see it says, the pins are active low. Active type means the on state. When the button is pressed, this equates to the pin being active. Describing active type as low means that when there is a low near zero voltage, the GPIO bus value will return true. You'll see this return of true next when we listen for our input. These configuration methods also each throw an illegal state exception for the same reasons discussed earlier. In this circumstance, we will group them together in one try-catch as a configuration error and again throw an illegal state exception, because if we can't configure our GPIO pin, then our app is useless. When using a GPIO pin as an input, you can register a callback for state changes. You create the callback like this, implementing the onGPIO edge method. If you only want a single callback, you return false from this method. However, we want to be notified every time the button is pressed, so we return true. The onGPIO edge method is passed the GPIO bus as a parameter. We can use this parameter to determine the current state of the GPIO peripheral. Let's do that now with this code. As you can see, when the GPIO's getValue method returns true, the button has been pressed down. This matches the discussion about active type we had earlier. When onGPIO edge is called and the GPIO's getValue method returns false, this means the button has been released. Let's now use the callback we have created and register our interest with the Android Things GPIO SDK class. Add this code to your onStart method to register the callback. We are using the onStart method as we want to be notified of button presses when our activity is in the foreground. This is slightly less relevant on Android Things as only one application should ever be installed, but it's still a best practice to future-proof your code. Once again, the methods we call throw an IO exception. If registering a callback throws this exception, then our app won't work, so we catch this and throw an illegal state exception, crashing the app to fail fast. The setEdgeTriggerType method is how we configure what callbacks we want to be notified of. Using the edgeBoth parameter means we will be notified when the button is pressed and also when the button is released. Relating this back to the active type discussion, we will be notified when the peripheral enters the active state and when it exits the active state. Finally, since we registered the callback in the onStart method, we should use the symmetrically matching pair from the Android lifecycle to unregister. Therefore, we unregister our callback in onStop using this code. Let's run our app and check the logcat for the messages showing our button is working. That's it. You now understand how the Android Things GPIO communication with input peripherals works. You can interface with hardware buttons and monitor for state changes, knowing when the button is pressed or not. This knowledge also transfers to other GPIO input peripherals, such as other types of hardware buttons, motion detectors, or light sensors.